Hey everyone, welcome back. This time we're doing a new topic. New topic is numerical integration. Now, last couple videos we talked about numerical differentiation, where you need to take the derivative. This time we're just doing the opposite. Now we're going to find the integral of something. Between the two of them, differentiation versus integration, you can almost always take derivatives of functions, right? If you have a function written explicitly, you can take the derivative of it. We saw that with numerical differentiation, we needed it when we had data sets, right? When we didn't have explicit functions. Now, even if you have the explicit function, there's no guarantee that you can analytically integrate a function, right? Like there's all kinds of functions that you cannot integrate analytically, but we can integrate them numerically. So between the two of them, it turns out that numerical integration is in fact far more useful and far more often used than numerical differentiation. We're going to use numerical integration to solve two types of problems. The first type, which is what we're going to talk about today, is going to be definite integrals. The second type, which is going to be the next couple of videos, we're going to be using numerical integration to solve differential equations. Now, the second one, honestly, this second one gets used very often in science and engineering, solving differential equations. So we're gonna spend a good bit of time on this, but let's go through a couple of methods for definite integrals, and we'll do also a screen cap video for both of these. We'll have two different videos. Now, before we dive into the definite integrals, let's talk about this numerical integration graphically. So when I say a definite integral, imagine that you have some function f of x, and we want to integrate this function over some bounds, a to b. Now, of course it depends, right? How complicated is f of x? Can it be integrated analytically? If you can integrate it analytically, congratulations, right? You do it and you find the answer. What if we can't? Right? That's where this numerical process is going to come in. And of course, we're going to have to come up with these algorithms. So let's do a plot of f of x. So we're saying x is on the horizontal and f of x is the vertical, and we want to integrate this function over some bounds, a to b. So let's put a first and b second. Here is the function f of x, and we want to know what the integral is of this function. Now, we know what the derivative of it is. Derivative would be the slope. So if I pick a certain point and I ask what is the derivative of the function, right? What is f prime of x? Well, obviously it changes at all points, but we know that it's going to be the slope. Integration is not slope. Integration is the graphical explanation of it is it's the area underneath the curve. So here is this would be f of b. This is our ending point, and it's the area up to b. So the integral is literally the area underneath this curve. You probably remember that from calculus class. But it's going to be exceptionally useful now as we approach these numerical algorithms, because we're going to start with some kind of graphical approach, and we're going to say, how can we calculate this using some kind of numerical process? So that's the goal, that's the point. Let me clean this up and we'll get started on the first one. We're focusing on methods for definite integrals today. There's three methods that we're going to do. Rectangular, trapezoidal, and Simpsons. Rectangular is the most basic, so let's start there. We're going to slowly build. So we're doing rectangular rule. So rectangular rule, rectangular method, right? Numerical integration. Let's put our diagram, and let's start here. So here is the function f of x. We know that x is on the horizontal, and we're measuring the value f of x. We said we want to do definite integral, right? We want the definite integral of f of x over the bounds a to b. So here's our bounds a to b, right? The rectangular rule, the claim is, what if we take this space? We know that we want to calculate the area under the curve, right, over these bounds a to b. What if we take this space between a and b and let's discretize it? Let's break it into segments. All right, we're going to break it into n number of segments. It just so happens that right now we have 1, 2, 3, 4, 5 segments. So in this example, we would say that n equals 5, where n is the number of samples. Next thing we need to specify is h. So h is the width or the step size between two of these entries. So h, I'm just going to say that h is step size. Okay. So you're approaching a numerical integration problem. You want to use rectangular rule. You have some knowledge of your function. You need to specify these. And clearly these two things are actually connected, right? A to b is probably fixed. We need to integrate some function over some bounds. If you specify n, you can calculate h, right? And obviously as n increases, then h is going to go down, right? Another way you could do it is you could specify some kind of maximum or minimum h, and from there you could calculate the number of step sizes. That's fine as well. So what we're going to do is we're going to discretize it. We're going to specify these two. And again, remember, we want to calculate the area underneath the curve. So what can we do now? Consider what we have available. We have f of x available. Let's say that we have the function. And the function is complicated enough that we cannot numerically integrate it, but we could always put in a value, right? I could say, what is f of 1, and I get a number. What is f of 2, and I get a number. That means that we're able to evaluate the function at these points. So we know what the value of f is at those points. And if we want the area under the curve, well, couldn't we take, let's go to the very first point, and let's just extend a line straight across, and then let's turn this into a rectangle. Again, write the name of the method, rectangular rule. Now, how can we calculate the area of this section? Well, this is just a rectangle, right? So what's the area of a rectangle? Area of a rectangle is a length times width, base times height, something like that, x times y. So what are the two dimensions of this rectangle? Well, the width is h, right? And again, you specified that. You have this knowledge. And then what's the height? Well, the height is f. And tell you what, I'm going to go ahead and label these points. Let's call this first one f0, and the next one is f1, f2, 3, 4, and f5. In this case, 5 is the last one. Notice that the height of this rectangle is f0, right? That's literally the height. It's the value of the function evaluated at the first, or the 0th, right, times 0. So the area of that rectangle is going to be h times f of, in this case, we're going to say 0. And that this would be, the area of the first one. What about the area of the second? Well, we could take this second one and we could extend this one across, right? And we can make a rectangle out of this one. And we can shade that. So what would be the area for this one? We would say area number 2. And again, the width of all of these, they're all constant. It's a constant width h. And then the height that we're using now is f1. And you can see that we could repeat this, right? Let's talk about limitations or error. We have no limitations on the number of data points. If you have the function explicitly, that means you create the data points. This isn't some, it's not like we're working with data sets here and we have limited information. One thing to take note of though, is that there is error, and I'm going to shade it in red. There is error on the top of the curve here. And this is, these are values that you are missing, right? Because F0 undershoots the curve at this point. And then there's also error on the second rectangle, and that error is on top, and that error is actually outside of the curve. So you are overestimating the integral in this approach, simply because the function is curving down, right? And we're holding that height constant. So we can see that there's a fair bit of error in this approach, regardless of whether you're undercutting or overcutting the curve. Next. Another thing to consider, notice that when we did these two squares, we started at the first point and then we went to the second, right? So that is called a, I'll tell you what, I'll put it down here. These two squares that I've done in blue, these are the left-sided approximation. And it's called that just because we're using the point on the left side, approximation. If this is the left side approximation, clearly we could do something else. What if, when we're doing these boxes, instead of choosing the point on the left, so instead of choosing F4, what if instead we chose the point on the right? We could do that. We just extend this line straight across and we make our rectangle like this. So the area, this was 1, 2, 3, 4, 5. So area number 5 is going to be H. And this time we chose the point on the right, F5. So H times F5. So what is this approach called? Well, if this one's left, this one is right. So here's our right-sided approximation. There we go. And of course, regardless of whether you did left or right, in both cases, there's a little bit of error from where you overcut or undercut the function. So shading this one in blue now, there's a little bit of error on top. So when we did right-sided here, we underestimated the integral. Now, we know that there's going to be error in this. How can we reduce the error in an approach like this? The error is all connected to these overcuts and undercuts, right? So really, we just want to reduce that as much as possible. How you control the error in these approaches is with, I'll put the box up here. This is what is going to control the error. The number of steps, and therefore the size of the steps. If you want less error, we need H to be as small as possible. The smaller that we make H, the more increments, right? And that's going to make the error be very small. Now, with that said, if we need a certain level of accuracy, or sorry, precision, right? More decimal points. If we need better precision, can't we just make H as small as possible? Just make H 10 to the negative 10th, something like this. Understand that if you make H very small, if you make N very large, you have to perform the multiplication, right? In order to find these areas and then add them all up. So the more of these there are, the more steps there are in the algorithm inside the loop. What we would really like to do is we would like to find a better algorithm with better precision, such that we don't have to drive H to be very small. We don't have to run it at 10 million steps. A better algorithm would let us run less steps, right, and get better precision out of it. So that's what we're going to see in the next couple of methods. But this is rectangular rule. All you literally do is you just take the width and you multiply it by the height, and that gives you the area for each one, and then you do a summation on all of those, and you get the area for the whole thing. Before we move on to the next one, let's take the math for the rectangular rule and let's lay it all out and let's see what comes out. We said that the area for a certain section is going to be H times F, right, times f of x, whichever f of x we've selected. If we're going to do that for every single section, then what happens when we add them all together? That means that the definite integral from a to b of f of x, right? This is what we're attempting to calculate. We're gonna say approximate is approximately equal to, so that's h times f0 plus h times f1 plus h times f2, right? And I'm going to say plus h. Let's do a dot, 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 right? We're going to skip to the end. And then this last one is hf of n minus 1. Let me do a capital N. Now, this one that I just wrote, this is the left-sided approximation. We can tell that it's the left because it started with the 0th, right? And then it ended before the last one. So this approximation is really, how can we simplify this? We can factor out the h, and then we could just say f0 plus f1 plus dot 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 f n minus 1. And if we wanted to, we could write it using infinite summation, something like that. What about the right-handed approximation? So f of x is approximately equal to, if we're doing the right-handed, that means we've skipped the first, but we now include the last one. So this is h multiplied by f1 plus f2, right? Plus dot, 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 f n minus 1. Oh, sorry, this time it's now just fn, the last one. Okay, and this makes sense. This is very obvious. You just take all these, you add them together, you multiply by h. Okay. This approach, though, of taking all these and putting them together, this is actually going to help us when we get to some of the later ones. So for now, it's very straightforward. Let's keep going. Second method of the day, trapezoidal rule. Now, what we're going to do, it's in the name. Last method was rectangular. We made rectangles. So this time, we're doing the trapezoidal rule. We are going to make trapezoids. Now, recall what a trapezoid is. Go back to your geometry class. This is a rectangle. I can make a trapezoid if instead of letting the top and bottom be parallel, instead I cut one of these sides off at an angle. Okay, so there's a trapezoid. It's still a quadrilateral, still a four-sided closed polygon. So what are we going to do here? Well, remember we want to evaluate the area under the curve. We're going to discretize this integral. So 1, 2, 3, 4, 5 sections. And instead of making rectangles, we're going to make trapezoids. This time we're going to use both points on the top. So F0 and F1. We know that the width of these is h. If we know F0 and we know F1, then I can draw a straight line between F0 and F1. And sometimes maybe that looks pretty good, right? Like this curve isn't too crazy, it's not too fast. I can do straight lines between all of these, right? Straight line between those, straight line between those. And this might be a little better. Consider you could have a function that is doing something very rapidly, right? You could have a function with a large hump in it, something like this, and you just perfectly missed it between two of your data points. And whoop, there you go. There's your trapezoid rule, and you completely missed this hump, right? There's always those dangers, and again, that goes back to how many of these discretized segments do we need? And of course, the more sections, the smaller the step size, the less likely you are to get caught by some weird behavior like that. Okay, so what we're going to do is we're going to calculate the area of this trapezoid. We're going to calculate the area of this trapezoid, etc., all the way down the line until we have done it for all of them and we can perform a summation on the total. So all we need now is we just need some way to calculate this area, right? So What is the area? Well, all of these, regardless of the values of F0 and F1 and whether positive, negative, right? Regardless of the values, we're going to make a trapezoid. So go back to your geometry class and find the equations for trapezoids. Notice you have H1 and H2. You have two different heights, and you have the width. So what is the area of a trapezoid? Well, you take the two heights, H1 and H2, and you average them, and you multiply by the width. So this is equivalent to taking these 2 points, averaging them, and then flattening the triangle. You know, it's not a great drawing, but what you're really doing is like you're taking this upper portion of the triangle and you're fitting it into this lower portion of the triangle. And then you just multiply by the width. So specifically for one of these then, what's the area? Let's say, here's a general expression of the area. What if I wanted the area of the first section? If I want A1, I'm going to take my two heights, and in this case my heights are F0 and F1. I'm going to divide those by 2, and remember what the step size is. The step size is this variable h, and then we would just multiply by h. And again, you just go down the line and you do that. Now, where do you get the values of F0 and F1? Well, you know f of x, and you know numerically a and b, and you have specified how many of these discretized sections there are. So you should know the value of all of your x's, as you go down the axis. So really all we're doing here is we're calling the function, right? And we're passing a value to the function. And then we can perform this summation. Okay, if you understand rectangular rule, you should be okay with trapezoidal. Let's go ahead and move on to the next one. Oh, wait, quick comment. This method, better or worse than rectangles? This method is better. Because we're cutting to the points, the error now exists between this parallel line, or sorry, the line at the top of the trapezoid and the curve. So I'm going to make this last one a little exaggerated. Let's say we're doing something like this, right? There's the trapezoid rule, and the function is going to have a little bit of error, right? Still on this side, maybe a little bit on that side. So there is, of course, still error associated with trapezoidal rule. It is significantly better than rectangular. Before we move on to the last one, before we finish trapezoid, let's list out all the math and talk about what the final summation looks like. Remember, we're doing this definite integral f of x, and we need some approximation of this integral. In the trapezoidal rule, this is what the calculations look like. We could write it as h over 2 f0 plus f1. This would be the trapezoid for the first section, right? For the second section, h over 2, and this would be multiplied by f1 plus f2 plus, and I'm going to ... h over 2, and then this is f n minus 1 plus f n. Okay, look at this. Make sure you agree with it, make sure it makes sense. Remember, for the first trapezoid, it needs the two endpoints, right? So that's f0 and f1. For the second trapezoid, the two endpoints are f1 and f2. So notice in this approach, some of these points actually get repeated. Notice that f1 is here twice. If we included the next term, f2 would have been there twice. If we included the term before this last one, we would have had another fn minus 1, right? So all of the terms, they end up being included twice with the exceptions of these boundaries. So the boundaries are only in this series the one time, and then everything else actually gets duplicated. So if you were going to distribute the h over 2, you would have two f1s. So the 1 over 2 would cancel. So this approximation, it ends up simplifying down to this. Let's write it as h over 2 f0 plus fn, and then plus h. This is f1 plus f2 plus dot, dot, dot. And then this one goes down to n minus 1. Okay. This then, this shows that when you actually go to put this in code, you need to run this portion inside of a loop, right? You're going to iterate over these f values, and then you can actually just directly call the first data point and the last data point as h over 2. And if you're integrating over the bounds a to b, then recognize that this part is h over 2 f of a plus f of b, right? And then plus, you bring this part down. So remember, a and b are your starting and end points, right? So you literally pass the values of a and b to the function f, add them together, multiply by h over 2. That's going to be your trapezoid rule. Okay, this is good. We're going to also do this on the last one. We're going to do this kind of final summation on everything, so we'll see how that one comes out. It's going to make it easier to calculate. Last method for the day. We did rectangular rule, we did trapezoidal rule. Last method is Simpsons. You can tell that Simpsons rule is the best because it was named after someone. So consider what we did in rectangular and trapezoidal. In the rectangular, we held the height constant, right? So we did just like a straight line right across. In the trapezoid, we did a line with a slope, right? So we had a constant line, we had a line with constant slope. You could also think of these as polynomials. This first one where it's flat, this one is a polynomial of order 0. The straight line going up, this one has a polynomial of order 1. Can we just increase the order of the polynomial? And if we increase the order of the polynomial, hopefully it's a better fit and we'll have less error. So let's talk about how we can do that. Here's our curve. We know that we're going to discretize it, so I'm just going to do 3 segments. We know that we can evaluate the function at these points. So here is f0, here is f1, etc. And of course, we're trying to calculate this area under the curve. Now, if we held this one constant, that would be rectangular. If we draw a straight line between them, there's our trapezoid. We know that both of those are okay. They'll give us an approximation. But if we're able to use a second order polynomial, that means a curve, right? Can we get some kind of curve that is going to fit the top of this segment? And if we can do that in this segment, then that means maybe there's a second order polynomial that we can use on this one, and a second order polynomial that we can use on the next one. Each of these polynomials are different. Each segment will have its own second order polynomial. The hope is that we can come up with some efficient way of calculating this second order polynomial that eliminates a lot of error and isn't so complicated that it's more computationally expensive, right, than just taking a rectangular trapezoid and decreasing the step size. So what we're going to do is we're going to generalize the second order polynomial across one of these segments, and then we're going to take that general expression and we're going to fit it together into some kind of summation, all right? And that's going to be Simpsons rule. So let me clean this up and let's talk about how we can generalize it. We want to generalize that second order polynomial. Here is a segment of your function. I'm just saying there's a point here and there's a point here, right? And we can write an equation for this polynomial. We have a general form of a second order polynomial, ax squared plus bx plus c. Now, there are 3 unknown coefficients, right? And it doesn't matter which segment of the function we chose. This is the general expression for it. There's always 3 unknown coefficients. Because there are 3 unknown coefficients, that means we need 3 equations to solve for those unknown coefficients. We're actually going to end up needing 3 points on this curve. So what I'm going to do is I'm going to put 3 points on this curve, and we're going to equally space them out. So we'll have a point in the beginning, we'll have a point at the end, and we'll have a point somewhere, okay, good enough. That's fine. We'll have a point somewhere in the about the middle. Now, let's do this. Let's draw the x-axis. I'm going to say that the one in the middle is at 0. I'm going to say that the one on the right side is at h, and the one on the left side is at negative h. And we're going to find the curve that passes through these 3 points. Now, an interesting point, because we're finding the curve over this from negative h now to h. Understand the step size now is 2h, right? In the previous examples, rectangle and trapezoid, we found the area for 1h at a time. Now we're actually going to be finding the area for 2h. It's going to affect a little bit in how we choose our step sizes. I'll give you those details in a bit. For now though, let's say here is f of negative h, here's f of 0, here is f of h. Good. And then this is of course on the interval negative h to h. Okay. What I'm going to do is I'm going to use this diagram to come up with a couple of equations. Let me clean this up and we'll write those. Using the diagram from before, let's take this equation, our general form of the quadratic, and let's take those data points from the last diagram and fit them into this equation. Now, the left-hand side y, this is the value of the function, right? So this is f of negative h, right? This is taking the place of y. And what I'm going to do is I'm going to take my x values and I'm going to plug them into this quadratic. So we have a times negative h squared, and then we're going to have, since it's negative, I'm just going to make this minus, so minus b times h, and then plus c. Next, the point in the middle was f of 0. So when you plug 0 into both of these, clearly you're just going to get c. And f of h now, we're going to get a h squared plus bh plus c. And of course, because this term, it's negative h squared, clearly this is going to simplify down to a h squared. Okay. There we go. Now, what do we need to do? Well, we have 3 equations. They're quadratic, right? But we have 3 equations, and we need to solve for these unknowns, a, b, and c. There's a bit of algebra involved. I'm going to magically erase, and we're going to skip those steps, and I'm going to give you the answers. So when you solve for the variables a, b, and c, this is what you get. A first, a is f of h plus f of negative h minus 2f 0. This is all divided by 2h squared. Next one, b. B is going to equal f of h minus f of negative h, and it's this quantity divided by 2h. And the last one, I'll put it here in the bottom right, c. We had this one already. We have c is equal to f0. Okay. What can we do with these equations? So these are our 3 coefficients. What we really want is we want to take this, right? This is the function. You can take this a and you can put it into this equation. You can take b, put it into this. You can take c, you can put it into this equation. And then we need to perform the integration. So put these in your notes. I'm going to erase. Let's move on. Let's do that. Let's take all of this stuff and let's put them into the function. So we're looking at the definite integral from negative h to h. Remember, we're not back to the main one doing a to b. We're still trying to generalize. So we're integrating from negative h to h, and we're integrating that, right? So I can just say ax squared plus bx plus c. dx. And then this is going to equal, we have this same integral, these same bounds, and I can literally write those previous definitions in here. I can say here's f of h, f of negative h minus 2 f0, all divided by 2h squared, multiplied by x squared plus dot, right? We know that you already have them written down, right? You can literally just take those and you can drop them in and you can write this expansion. If you do that, you can do some rearranging, right? And then you can actually perform the integration. Now, you're performing it on the variable h, right? So when you do all of this, when you put all these terms in, we're going to even block this thing off and say, dx. So we're going to drop in all the terms, and then we're going to perform the analytical integration. Here's what you get. So this is equal to h over 3 f negative h plus 4 f of 0 plus f of h. Okay. Now again, this was just this little piece of the whole puzzle, right? For a single section where you're using a second order polynomial, this is what you get. There's a single f of minus h, there's a single f of h, and then we have 4 f0. And then the whole thing is scaled by h over 3. Okay. We need to take this now, and we need to put it back into that the overall idea of Simpsons rule, right? So let me clean this up, and we'll move on. This is the equation that we had before. The left-hand side, all I've done now is I've replaced it with f of x, right? If you want to evaluate the function over some bounds, then this is approximately this amount, right? And again, this is the little snippet. We're just going from negative h to h. What happens when we want to do the whole thing? Well, we know that our function, we're discretizing it, right? And we know that in order to do this segment, you need the function evaluated at 3 points. So if here is f0 and the next one is f1 and the next one after that is f2, then Simpsons rule is actually going to calculate the area of this region all at once, okay? And F1 is now the midpoint of that block. F0 is the beginning and F2 is the end. So we're gonna integrate all of this at once. And then the next round after that, we would have F3, okay? So there's F3. And then the next point after that would be F4, and we would integrate the area underneath all of these all at once. Okay, so the first section goes from F0 through F1 to F2. The section after that starts at F2, it goes through F3 and then to F4. So when we start writing the total, it starts looking like this. We still have this function. We're still performing a definite integral. And remember that we want f of x dx over the bounds a to b. So if we're going to apply this now to all of them, here's what it looks like. We're going to have h over 3. The first section, we will have, let's see. Let's do it by section. I'm going to break it up by section. So the first section is going to be f0 plus 4 times f1 plus f2. Okay. There's that integral for the first section. Next, second section, we would start with f2 and we would go through f3 and then we would end with f4. And then we would start with f4 and we would go through f5 and then we would end with f6 plus dot, 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 okay? And then what's the last one look like? Well, we know that the last one is ending with Fn, and it's going through the point immediately before that, and it's going through the point before that. So we have f of n, and then we have fn minus 1, and we have fn minus 2, right? And in each one of these, it's 1, 4, 1, 1, 4, 1, 1, 4, 1, right? The same pattern is repeating now. What if we took this whole thing now and we started adding up all the terms, right? We got rid of the parentheses, this kind of internal arrangement. If you look, F2 appears twice. F4 appears twice. F6 would appear twice. N minus 2 would have appeared in the one before it. So we have a pattern that arises, and that pattern is the very first and the very last terms, these only appear once. The odd terms, F1, F3, F5, and when I say odd, remember that there was a 0, right? The F1, F3, F5 terms, these all appear 4 times, right? There's a 4 in front of it. And then the even terms, not including the boundaries, right? The boundaries are the exceptions, but the even terms, F2, F4, F6, these all appear twice. So what does this look like when we start adding it all up? We would have an F0, we would have 4 F1s, we would have 2 F2s, 4 F3s, 2 F4s, plus dot, 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 and then I'm going to just drop down. There would be 2 Fn minus 2s, there would be 4 Fn minus 1s, there would be a single Fn, and that would close it off. So this is that same set of terms. We've just gotten rid of all the parentheses. Okay. Next, let me go ahead and give you this h. Now, in the previous approaches, h was equal to b minus a divided by n. It's a nice fancy way to find it, right? You find the width and you just divide by the number of increments. This time, because each integration is actually several points, h is going to equal this, b minus a over 2n. And again, this is coming out of the fact that we're integrating over 3 points, right? We're doing F0 to F2 all at once. So this is just a little snippet, small change in your code. Okay. We have this. Can we clean this up just a little bit more to make the algorithm easier? Sure. Let me erase. Okay. Same equation. All I'm doing now is I'm cleaning it up just a little. All right. So Simpsons rule, we saw that there were some terms with a 1, some terms with a 4, some terms with a 2. You can apply Simpsons rule as kind of like a triple pass. So what's the first section of this one is going to be the boundaries. So F0 plus Fn. Okay. Again, we saw that there was only one of each of the boundaries, so this is fine. Next, let's do 4h over 3, and then this is going to be F1 plus F3 plus F5, right, plus dot, dot, dot. And then the last piece is going to be 2h over 3, and then this is going to be the even ones, F2, F4, F6, plus dot, dot, dot. Okay, good. Next, let's talk about, let's talk a little bit about the pseudocode. For these, let me get this cleaned up. We'll list out some pseudocode and that'll be it for the day. The pseudocode for these approaches of numerical integration are fairly straightforward. There's only a couple steps. The first steps that you need to do is you need to specify or ask the user, I'm just going to say specify. You need to specify either n, the number of steps, or h, the step size. Depending on which one of those you specified, you then calculate the other one. So you calculate n or h using the input from number 1. Okay. And then what kind of equations do we have? Let's say that you specified n, and then I'll write the equations underneath. You could have h is equal to b minus a over n. This is rectangular rule or trapezoidal. Next, you could have h is equal to b minus a over 2n, and this would be Simpsons rule. Okay. After that, the algorithm is really just iterating over n points. Right now, you just iterate down the length of these points. Using f, let's say, as a function call, and perform. This is getting kind of small on the bottom. It's the last step, though. We're gonna call f. We're gonna use it as a function call, right? You just feed values into it, you get numbers back. And what we want to perform, it's not just a summation. We want to perform a weighted summation. And all I mean by a weighted summation is if you go back and you look at the equations we derived, it was 1 of these plus 4 of these plus 2 of these, etc. So it ends up being a weighted summation of these function calls. So this is all there is to the pseudocode. You can sort out these first 2 very easy. This third one, honestly, is fairly straightforward as well. You can use some looping structure, a for loop or a while loop, something like that. Just be cautious, right, of how you identify the weighting. Is this point that I just called, right? Is this f? Does this one get multiplied by 1? Does it get multiplied by 4? Does it get multiplied by 2, etc.? Okay. All right. I think that's it for these. What is coming next? We're going to do a screen cap video on the performance of each of these algorithms. We're going to do rectangular, trapezoid, and Simpsons all together. And as we've done in the past, we'll do it in MATLAB. I'll have a little visualization so we can see things like the error, what it really is. After that, we're actually going to stick with numerical integration for about another week. This is how you solve definite integrals. The next section is going to be numerical integration of differential equations. And that's a lot of fun, I think. So, have a good day. Yeah, I'll see you next time. Stay safe.